Hi everyone, I'm Cheryl. The next exercise is an optimization problem. Usually when I start optimization problems, I like to start with a picture. And I've already put a picture on the board for this problem. What we're asked to do here is we're supposed to look at the graph y equals x squared and find a point on that graph that is as close as possible to the point 0, 3. So here's y equals x squared, it's just a parabola. And here's my point 0, 3. So I'm looking for the point that is as close to this point 0, 3 as possible. All right, after I kind of have a visual and have an idea of what I'm trying to find, the next thing you have to do is to come up with a formula that you're going to be minimizing. Well, in this case, I'm looking for the minimum distance. So I need a distance formula. Well, I know that this is the point 0, 3. This point, though, I have no idea what it's going to be. So I'm just going to label that xy. So the distance formula tells me that the distance between any 2 points is the square root of the change in x squared plus the change in y squared. For my particular example, I'm going to write this as x minus 0 plus y minus 3, quantity squared. Okay, and I can simplify this a little bit, and I'm left with x squared plus the quantity y minus 3 squared. Okay, so now I have my formula that I want to minimize. The next thing I have to be concerned about is I would really like this formula to be a function of a single variable. Notice I have both x's and y's in my formula, so I want to write everything in terms of x's or everything in terms of y. I think in this case it's going to be easiest to replace the y with an x squared, because I know that that point is on the graph y equals x squared. So let's do that substitution. So I now have the square root of x squared plus the quantity x squared minus 3 quantity squared. And at this point there'll be some more simplification that I can do. So I'll write this as the square root of x squared plus x to the 4th minus 6x squared plus 9. That's just using FOIL on that x squared minus 3 quantity squared piece. And now I can simplify even further till I have the square root of x to the 4th minus 5x squared plus 9. Okay, I have my function as a function of a single variable x. The next thing I want to do is to find where the relative minimums occur. All right, well that means I need to find critical numbers. So I'm going to take the derivative. Now, if you think a little bit ahead, you might notice that taking the derivative of this function is going to be fairly complicated. And I know that the square root function is a strictly increasing function, so that means that whatever values are going to minimize the inside part, the x to the 4th minus 5x squared plus 9, will also minimize the square root function. So I'm going to take a little shortcut, and I'm going to let f of x equal just the inside portion of that function, x to the 4th minus 5x squared plus 9. And I'm going to try to find the minimum values of this function. Okay, so critical numbers. We need the derivative. The derivative will be 4x cubed minus 10x. We know critical numbers happen when the derivative is 0 or when it's not defined. So we have to ask ourselves those same two questions. When is the derivative 0? And when does that derivative not exist? Okay. So when does the derivative equal 0? Well, 4x cubed minus 10x equals 0. That's a polynomial. We're going to solve by factoring, first of all, so that I can take an x out of both terms. And I have x times the quantity, 4x squared minus 10 equals 0. And if I have two things multiplied together that equal 0, I know one of them has to be 0. So either x equals 0 or 4x squared minus 10 equals 0. Well, this part's already set for me. I know that there's a critical number at 0, but I'm also going to consider 4x squared minus 10. To solve that, I'm going to add 10 to both sides and divide both sides by 4. So that will give me x squared equals 10 over 4. That will reduce to 5/2. And I can take the square root of both sides, and I have plus or minus the square root of 5/2. Now, if you like using decimals, that's approximately plus or minus 1.58. Okay, now that I know my critical numbers, I need to find out when I have a relative minimum or when I have a relative maximum, or maybe nothing at all. Just because it's a critical number doesn't guarantee that it's a minimum or a maximum. So we're going to take our information and we're going to put it on our chart to help us figure out where those minimums actually occur. So the first interval that I'm going to look at are going to be values of x less the negative square root of 5/2. The next interval will be everything between negative square root of 5/2 and 0. So I'm going to look between square root of negative 5/2 and 0. Next, I'll go from 0 to the square root of 5/2. And finally, I'll look at the interval where x is greater than the square root of 5/2. Okay, so we need a test value for each of these intervals. So let's start with the interval, any value of x that is less than negative root 5/2. So pick something really easy. Maybe x equals negative 10. Okay. So remember what we're going to do. We're going to plug that into the derivative to see what the sign is. So here's my derivative. And if I plug in a negative 10, I'm going to end up with negative 4,000 plus 100. That's definitely a negative number. So my conclusion is that my function is decreasing on that interval. Now let's pick something between negative root 5/2 and 0. Since I already know that's approximately negative 1.58, how about negative 1? That will be an easy thing to test. So I'll try negative 1. And when I plug it into the derivative, I'm going to have negative 4 plus 10. That's definitely a positive number, which means that my function is increasing on that interval. Okay, I need to pick something now between 0 and the square root of 5/2. Well, let's try positive 1. If I try positive 1, I'll have 4 minus 10, which is a negative number. Because it's negative, I know my function is decreasing. Now I need to pick something bigger than the square root of 5/2, so let's try positive 10. If I try positive 10, I'm going to end up with 4,000 minus 100. That's a positive number. And so my function is increasing. All right, so notice that I have a change in sign from negative to positive right at the square root of negative 5/2, which is telling me that there's going to be a minimum value there. So there's a relative minimum at x equals minus the square root of 5/2. Okay. Notice there's a change from positive to negative, but that's going to give me a maximum value. Okay. And I'm not interested in maximum values. I want something where the distance is the smallest. But if I go from negative to positive, I'm decreasing and then I'm increasing again. That's going to give me another relative minimum. So I'll have another relative minimum when x equals the square root of 5/2. Okay. Now, if you want to, you can actually calculate the y value for each of these points. So I'm going to have the point minus the square root of 5/2. And if it's on that function, all I need to do is square that. So that'll be the point negative square root of 5/2 and 5/2. The square root of 5/2, when I square it, I get 5/2. So it turns out that there are actually 2 points that are as close as you can get to 0, 3. And because of the symmetry of my graph y equals x squared, that makes sense. I'm going to have one on one side and one on the other side. So negative 1.58 is going to be right about in here, and we're going to go to 2.5, which is right about here. So this is going to be the distance that is the closest if you move to the left. The second option is root 5/2, which is again about 1.58. So that puts me right about here on the x-axis, and 2.5, which is going to put me right about here. And so that's the closest point. And now we have it. I hope that was helpful. Thanks.